Rigid bodies in equilibrium. A body is considered rigid if the distance between 2 points on it remains constant in time, no matter what external forces act on the body. That is, the body doesn't change shape. A rigid body is in equilibrium when it has 0 translational acceleration and 0 angular acceleration. Remember Newton's second law? It tells us that an acceleration is caused by a net force. So, for a rigid body to be in equilibrium, the net force applied to it must be 0. Remember that the net force is the sum of all of the forces. So, just because the net force on an object is 0, that doesn't mean that no forces are acting on the object. It just means that the forces in question balance each other out. It also means that if we're working in 2 dimensions, then the net force on the body in the x direction needs to be 0, and the net force in the y direction needs to be 0 in order for the body to be in equilibrium. The angular acceleration of an object is affected by the torque on the object. So, in order for a rigid body to be in equilibrium, the net torque on the body must be 0. When working problems with forces and torques, you want to know if you can apply equilibrium conditions to the problem. To find out, first draw a free body diagram of the object in question, showing all external forces acting on the body. Next, find the net x direction force and the net y direction force. Then, if the translational acceleration is equal to 0, you can set the x and y direction net forces equal to 0. Next, if the body has an angular speed, decide where the axis of rotation is, and calculate the torque on the body from each applied force. If the angular acceleration of the body is 0, you can set the sum of the torques on the body equal to 0. Then you can solve all the equations for the unknowns. Let's try an example problem. The rectangle shown has 2 forces acting on it. Force F1 with a magnitude of 14 newtons is acting to the right at corner A, and force F2 with a magnitude of 16 newtons is acting upward at corner C. The axis of rotation is in the center of the rectangle, going into the screen. The distance between corners A and B is 1.5 meters, and the distance between corners B and C is 0.76 meters. A new force, F3, is applied to corner B, either upward or downward. What do the magnitude and direction of F3 need to be in order to keep the rectangle in equilibrium? Okay, what are we given? We have a force F1 of magnitude 14 newtons acting to the right at corner A. We have a force F2 of magnitude 16 newtons acting upward at corner C. The axis of rotation is in the center of the rectangle. The distance along the long axis of the rectangle is 1.5 meters. Let's call that D1. And the distance along the short axis is 0.76 meters. Let's call that D2. And what are we looking for? The magnitude and direction of F3. We know that it's either upward or downward at corner B. Okay, so far we've drawn a free body diagram of our object with the forces acting on it. Next, we need to find the net x direction force and the net y direction force. To do this, we need to specify which are the positive x and y directions. Let's say that up is the positive y direction, and to the right is the positive x direction. Force F1 is acting in the positive x direction, and it's the only force acting along the x-axis, so the net x direction force is equal to F1. F2 and F3 are both acting along the y-axis. F2 is acting in the positive y direction, but we don't know yet which direction F3 is acting in. We can say that the net y direction force is F2 plus F3. Then, if we find F3 to have a positive value, we'll know that it's acting upward. If we find a negative value for it, we'll know that it's acting downward. Next, if translational acceleration is equal to 0, we can set each of these equations equal to 0. We're looking for the third force that would keep the rectangle in equilibrium, which means the translational acceleration would be equal to 0. So we can set these equal to 0, giving us two possible equations to work with. Now we find the torque associated with each force. Torque is equal to the magnitude of the force times the lever arm, and the lever arm is the distance between the line of action for the force and the rotation axis. So let's draw the line of action for force F1 and the lever arm for force F1. Remember that torque is considered positive if it would result in counterclockwise motion, and it's negative if it would result in clockwise motion. We can see that force 1 by itself would result in clockwise motion of the rectangle, so torque 1 is equal to minus force 1 times lever arm 1. Next, we'll draw the line of action and lever arm for force 2. Force 2 by itself would result in a counterclockwise motion, so torque 2 is equal to force 2 times lever arm 2. Since force 2 and force 3 share the same line of action, they also share the same lever arm. Since we don't know which direction force 3 is acting in, we don't know if torque 3 is positive or negative. For now, we'll assume that it's positive from an upward force. If we find that F3 has a negative value, we'll know that F3 is actually pointed downward, and the torque from it is negative. So we'll write torque 3 as force 3 times lever arm 3. We add these together to get the sum of the torques. Now, if the angular acceleration is equal to 0, we can set the sum of the torques equal to 0. Equilibrium means that the angular acceleration is 0, so we'll do so. Now we can choose an equation to solve. We'll only need one of these, which means that we did some extra work here. We did that because I wanted to take you through all the possible helpful steps. We'll just use the third equation that sets the sum of the torques equal to 0. We're looking for F3, so we'll first solve this equation for F3. Now we need values for L1, L2, and L3. Looking at the diagram, we see that L1 equals 1/2 of the distance d2, and L2 and L3 each equal 1/2 of the distance d1. So we plug these in for the lever arm terms, getting this expression. Now we plug in our values for F1, F2, d1, and d2. And finally, we can use our calculator to solve, getting a value of minus 8.9 newtons. Remember, getting a negative value for this force means that it's directed in the minus y direction, which is downward. So our final answer for the third force is 8.9 newtons downward.